So even though all these interactions are extremely complex, we have very diverse set of contributions. But at the fundamental level, so we do see there is a common structure that underlies all these different relationships, and that structure is causality. So, for example, we can take, let's say we suppose we produce a very powerful scientific model for materials, and we can analyze the causal relationship to figure out who are the contributors of this final particular science model. For example, to have this final model, you need to have a base model, for example, a deep sea. And for that, you need to have a huge set of, for example, GPU clusters to do this training process, so which involves many different GPU nodes. And to further have that, you need to have the data set to help with the training. So the data sets are, for example, need to be cleaned and prepared and pre-processed, and then you have the raw data, right? So which is contributed by maybe thousands of millions. So all this relationship can be represented by a causal graph, which relates directly to the thinking graph. And all the vertices in this graph are events, and the edges are the causal dependency. This kind of causal graph has very wide applicability beyond, for example, traditional financial applications, like for traditional blockchains. So we already mentioned that you can use this causal graph for AI. But you can as well use it for example, social process, where we have different people interacting with each other. There's also you can do a causal graph, for example, social. So there is one inherent problem with this causal graph approach, which is scalability. Because the more events happening in the system, we essentially grow your causal graph bigger and bigger. So if we want to, for example, transmit this causal graph in every possible interaction, then it becomes intractable. And there's a second problem, which is if we want to use this causal graph in, for example, a fully decentralized environment, then we need to be concerned about, for example, adversaries manipulating graph data. To solve all these problems, the Hetu team has done quite extensive research, and we have come up with very interesting distributed protocols to address some of these challenges. So the key here is that we saw that fundamentally, right, so no matter how complex your system or your this contribution graph is, and there's always communication. Right? So for example, you need to usually send your data to the GPU nodes. And the GPU nodes, when they compute, right, they need to send your partial gradients to the other GPU nodes to actually derive the final model. Right? So throughout this communication process, what we do is we leverage a data structure called logical clock for a compact representation of the causal graph. And we leverage some cryptographic mechanism to build a verifiable logical clock for ensuring the security of this causal graph, so that adversaries cannot just manipulate the causal graph. So building on top of our verifiable logical clock and causal graph, we built a new type of consensus protocol called proof-of-causal graph. So this is very different from traditional kind of blockchain consensus like proof of work, which nodes just perform, for example, hashing algorithm. And so here, block proofs are essentially very logical clocks that prove the extension of the causal graph. Right? So that is, these validators are able to produce this kind of extension to the existing causal graph to build further and further onto existing graphs. And so by using this kind of proof of causal work, we incentivize building upon the existing graph, right? So, and that is called extending causality. So this is, the notion is very similar to proof of use proof. Right? So essentially what we want to do is we want to incentivize the user to perform all this useful causality work to extend the existing causal structure. And the other difference, major difference from existing blockchain structure is that this causal graph is inherently will have many parallel graphs. Right? So which also means that forks are common and not the exception in this kind of structures. And which graph should you extend on? Right? So that is very subjective. Right? So there is no objective function to decide which graph is the correct graph. So you can decide you want to extend one particular node on this graph because you believe that that is a more correct version of that particular computational process. That is totally fine. Some other people may have other opinions. They may extend on other part of the graph in that is more correct. And so as the protocol itself doesn't really define what is correct or wrong. But eventually we do have something called an intersubjective consensus, meaning that there is collective agreement by participants who have common values. That means a set of people or a bigger set of people who think one part of the graph is more like appropriate, and then they will work on that graph accordingly. So one really important application of or implication of this causal work and causality graph is that we can do proper value distribution. So causality in causal graph essentially implies contribution. Remember that this causal graph has edges and vertices, right? So we can backtrack these. For example, we can take one final node in this causal graph. For example, that is a creation of a big model. Right, so you can backtrack this causal graph, and throughout this traversal, the vertices are the contribution of this final node. And by using the subject consensus, we actually incentivizes impactful contributions. Right? Impactful means that other people are following particular subgraph, so that means you are making a more impactful contribution. So by using HETUProtocol, we ensure decentralized, fair, and secure way of doing this value distribution. So now we're using HETUProtocol in causal graph. Right? So we have used several key infrastructure in our AI science operating systems. First is the Hetu model DAO. So this model DAO, the goal is to compute powerful AI models. As I already said, AI models stem from a broad set of contributions. For example, from the base models, and you can do fine-tuning and do distillation and a bunch of other techniques to derive virtual models. And so when we actually say some virtual models for particular scientific areas is really, making a lot of impact, generates a lot of value, so we shouldn't forget about all these previous models that are part of the evolution process that generate this final model. And so this model graph basically keeps track of this particular evolution process. So that means by using this model graph and model graph, we're able to incentivize contributions that lead to AI breakthroughs. So that actually incentivizes people and DAO to create really, really powerful AI models. So the final outcome will be we're able to compute these powerful AI based and virtual models in a fully decentralized manner. So not just AI models, we can also leverage our causal graph to build, for example, a social graph, and then to help maintain the social contributions of different projects. And as I said, in a scientific process, there's not just the AI model part, but there's also the human interaction part. And so you have your scientists, like collaboration, and then you have peer review process, And then within, for example, a big model DAO, and we also have a lot of these DAO members who contribute to the social process. For example, inviting other people joining the DAO and advertising the AI model on the social platforms. And so we create this Hetuverse who can help keep track of all these social contributions to these models and DAO. So here, let me just give you a high-level overview of the entire architecture for our Hetu AI for Science operating system. So on the bottom layer, which is our ground layer, so we build our consensus layer that includes things like causal work and our causality graph. And on top of that, we have some key execution layer, which includes the model graph and the social graph and some governance. The decentralized governance layer. And one step further, we have our framework layer. So here we build several key frameworks. For example, AI middleware, where we build our infrastructure on MCP, like AI agents, and inference and training infrastructures to facilitate users and, for example, scientists. And we also build a parallel chain. So it's a very, very high performance, high throughput chain, similarly based on a DAG protocol. So this DAG protocol ensures really high chain throughput, but we also look at new research into how we actually get finality in this chain to become faster. So for example, we are leveraging speculative execution to do fast interactive finality to ensure that we can have more like interactive process with this change function. And on the top layer, so we have our integration layer, which includes a model as a service platform, our dashboard, and all other kind of service integration using our APS and CPS system. Due to time constraint, I wasn't able to elaborate on all these different components, but if you're interested, feel free to reach out to us. I would like to conclude. Right? So today I discussed the Hetu AI for Science operating system. And so we look at the AI for Science scenario and particularly the central problem in this process. And to tackle this problem, we introduced a new construct called the causal graph that tracks the event causal dependencies. And based on this causal graph, we designed a new type of consensus mechanism called POCW, and which applies intersubjective consensus. And using causal graph and POCW, we built several key infrastructure, including a model DAO, which we use it to co-build powerful AI models. And so with that, I would like to end my talk here. But if you're interested in our project, feel free to scan the QR codes for our website, our Twitter, and our GitHub account. Thank you.
Our next panel for AI, redefining the AI economy with identity, attribution, verification, and payment by Scott, the co-founder of and CTO of